Hi everyone, hope you are following the concepts in electrochemistry, right? Last class we discussed about the variation of molar conductivity with dilution, and we saw for a strong electrolyte, and we plot a graph, hope you are remembering that, in which the molar conductivity has only a slight increase in the dilution, isn't it? Now today we will see the variation of molar conductivity for a weak electrolyte. Okay. So last class we have seen we plot a graph with root C, that is concentration with molar conductivity, and you got a straight line for a strong electrolyte, isn't it? Then we extrapolate it or extend it and you got lambda 0, which means the C or the concentration tends to 0, correct? Now we will see the same thing for a weak electrolyte. Okay, now if we draw a graph as root C along the x-axis and lambda m along the y-axis, we see as the concentration decreases, that means as the dilution is increasing, what happens? We will get a parabola like this. See? That means as the concentration is decreasing, the lambda m is increasing, and see here there is a steep increase in the molar conductivity. See, it is going parallel to the y-axis, it is not getting touched, isn't it? So it goes on increasing. A very steep increase is there for the molar conductivity in the case of a weak electrolyte. Or I can say if C tends to 0, what happens? There is a sharp increase in the molar conductivity, and see here there is only a slight increase in the conductivity in the case of a strong electrolyte. Now we have to see the reason for this. As we studied last class, what was the reason for that slight variation in the molar conductivity of a strong electrolyte? What was the reason? The reason was not based on the DOD, isn't it? DOD means degree of dissociation. It was purely the attractive force. Why? Because in the case of a strong electrolyte, there is 100% dissociation. So there is no point of degree of dissociation. So there is only chance for the increase in the molar conductivity is only the attractive force. There is a weakening of attractive force, thereby the conductance increases by the ions increases. That's all. But when you come to the weak electrolyte, it mainly depends on the DOD or the degree of dissociation. So I will explain how there is a sharp increase in the molar conductivity. Okay, that is, you know, a weak electrolyte means what? AB reversibly giving A plus plus B minus, correct? That means there is always have a tendency to form this A plus and B minus to form an undissociated AB, isn't it? Now what happens is, on dilution, that is for example if we are adding more and more water or solvent, what happens? This A plus and B minus, due to the dielectric property of water, the force gets weakened. The force of attraction gets weakened. Now what happens if the force of attraction gets weakened? The ions are free to move. That means the A plus and B minus won't come each other to form an undissociated thing. It will act freely. It can move freely in the electrolytic solution. Okay. Now what happens when this concentration tends to 0, or I can say at infinite dilution? Infinite dilution is nothing but the molar conductivity at 0 concentration. And another name for molar conductivity at 0 concentration, you call it as limiting molar conductivity. Okay, so at infinite dilution there is a sharp increase. That means if more and more water is added or solvent is added, what happens? This A plus will remain as such and B minus will move as such, isn't it? So there is a free flow of A plus and B minus. Now what will happen here? This is same as the weak electrolyte is acting as a strong electrolyte, isn't it? What happens to a strong electrolyte? 100% dissociation. Now see what happens for an infinite dilution for a weak electrolyte. The same thing, 100% is dissociating there, isn't it? So you can say at infinite dilution, the weak electrolyte act as a strong electrolyte. Clear? But the problem is how you will calculate the lambda 0 or the limiting molar conductivity of a weak electrolyte. In the case of a strong electrolyte, we can have from the graph, that is C, that is lambda 0 and on extrapolating you get the value of lambda 0. But here, how can we extrapolate it, because it is going steeply, it's going parallel, you can't cut it on the intercept on the y-axis. So that's a problem. So for that, a scientist called Kohlraasch has obtained a law which is called as Kohlraasch law of independent migration of ions. What do you mean by independent? That's why I have already told you, on infinite dilution, the A plus and B minus are freely moving. That is, independently they are migrating. That's it, isn't it? So he obtained a law which is called as the Kohlraasch law of independent migration of ions. So now we will see. Now you got an idea how the molar conductivity steeply increases on dilution. That is basically the point is of the DOD, that is degree of dissociation. The degree of dissociation increases, thereby the molar conductivity increases, or the number of ions increases, thereby the conductivity increases. Now we will see how to calculate the limiting molar conductivity of a weak electrolyte. For that, we will see what is Kohlraasch law. Hope you understood. Is it clear? Okay. Now we will move on to Kohlraasch law of independent migration of ions. Kohlraasch law of independent migration of ions. Now, what this law states is, the law states that the limiting molar conductivity, what is it? Lambda 0, isn't it? The limiting molar conductivity of any electrolyte, very important, any electrolyte means what? This is applicable to both strong as well as weak electrolyte. It is applicable to both strong and weak electrolyte. Okay. Now, Kohlraasch law states that the limiting molar conductivity of any electrolyte, whether it is a strong or a weak electrolyte, is equal to the summation of what? The individual cation as well as the anion of that electrolyte. Once again, I will tell you with an example. For example, if I say lambda 0 m of NaCl, this is a strong electrolyte. Now, Kohlraasch says that the limiting molar conductivity of NaCl is equal to the summation of what? The summation of the lambda 0 of Na plus, that is the respective cation, summation means addition, plus lambda 0 of Cl minus. See, this is what Kohlraasch law states. That means it states that the limiting molar conductivity of any electrolyte, for example, if I can say a weak electrolyte like CH3COOH, how you can do it? That is, the limiting molar conductivity of any electrolyte is the summation of the contribution of the limiting conductivity, molar conductivity of the respective cation as well as the anion. It's a simple law. That is lambda 0 of CH3COO minus plus lambda 0 of H plus. So you can calculate the lambda 0 or limiting molar conductivity of both a strong electrolyte as well as a weak electrolyte. Strong electrolyte, even you can plot a graph and calculate the lambda 0 here. But for a weak electrolyte, you can't do that. For that weak electrolyte, you can apply what? You can apply the Kohlraasch law. Correct? So that is Kohlraasch law. That is the summation or the contribution of both the cations as well as the anion. I have already told you that in infinite dilution, the weak electrolyte acts as a strong one, isn't it? That is why we are able to apply this law. Okay. Now, if an electrolyte is, in a general way I can say, or I can write, if an electrolyte is dissociated into, for example, nu plus cation, stoichiometry, and nu minus anion, then how will you write the general equation? For example, I can give an example like calcium chloride. See, for example, the case of calcium chloride, it gets dissociated into what? Ca2 plus 2Cl minus. See, there is one cation and two anion. So, how will you represent the Colbrelj law? You can represent the Colbrelj law as lambda 0 m is equal to nu plus of lambda 0 Ca2 plus, isn't it? Plus nu minus of lambda 0 Cl minus. Now, what is nu plus here? That is 1, isn't it? And what is nu minus here? Anion, that is 2. Isn't it? So, in general you can say or you can write what? Lambda 0 m is equal to nu plus of lambda 0 cation plus nu minus of lambda 0 anion. So, this is how you calculate the limiting molar conductivity of any electrolyte, whether it is a strong electrolyte or it is a weak electrolyte. You got it? Okay. Now, for board exam, this is a simple numerical in electrochemistry. You will find it very simple. Okay, so I will give you the numericals in a separate session, as I have already told you. Okay, numericals we will do later. So this is the Colbrelj law. Now, having said this, you now know what is lambda m and what is lambda 0 m. Correct? You know this. Now, if you know limiting molar conductivity as well as the molar conductivity, you can find alpha. What is alpha? Degree of dissociation. Now, alpha is equal to lambda m by lambda 0 m. Very important. Numericals can come. Just study the equation. Alpha or degree of dissociation equal to lambda m. What is it? Molar conductivity divided by what is lambda 0 m? Limiting molar conductivity. Correct? Now, if you know alpha, you can very well find Ka. What is Ka? Ka is the dissociation constant. Last class we studied, isn't it? Dissociation constant, how? You have a formula Ka. I will write here itself. Ka is equal to C alpha square by 1 minus alpha, equilibrium. Last year's equilibrium chapter. C alpha square by 1 minus alpha. Now you substitute the value of alpha in this, you will get or you can find what? Ka or the dissociation constant. So if the question is asked, write two applications of Colbrelj law. Two applications of Colbrelj law. First is you can find what? You can find the lambda 0 of an electrolyte, whether it is weak or strong electrolyte, lambda 0, and second you can calculate alpha as well as Ka. So these are the two applications of Colbrelj law. So that's all about this variation of molar conductivity for a strong electrolyte as well as a weak electrolyte. Now here it comes the end of the qualitative aspect of electrolytic cell. As I already told you, there are two phases. One is the qualitative aspect and other is the quantitative aspect. Now here till here it was a qualitative aspect. Now we will see what are the quantitative aspect of this electrolytic cell. Now there also numericals will come. There we mainly concentrate on Faraday's law. There are two laws implemented by Faraday, that is Faraday's first law and second law. Based on that, questions will be asked. Now today we will see the introduction of an electrolytic cell or electrolysis. Okay, and in the next class we will talk about more on Faraday's laws of electrolysis. Okay, now if I say about electrolytic cell or electrolysis, in the 10th standard you have studied. So it is a recap of the 10th standard, that is electrolysis. Just to have a feel of this. Okay, then we will pass on to the Faraday's law. Now in electrolysis, in the 10th standard you have studied refining, isn't it? Refining of copper, electrolytic refining of copper, isn't it? Now what you have done, you have taken an electrolytic cell, correct? Then there are two electrodes, both copper, that is anode and cathodes are copper, and there is an electrolyte, that is the salt of that is copper sulfate. You are remembering, I hope. Then we know electrolytic cell means what? The power supply is given externally, isn't it? So here the anode and cathode, this is anode and this is cathode. Okay. Now cathode is negative and anode is positive. See? That is electrochemical cell, it was opposite. Anode is negative and cathode is positive. Here anode is positive and cathode is negative. And last class again I have mentioned what in electrolytic cell or in electrolysis a DC current is applied. Why? Because when DC current is applied, the electrolysis takes place and the deposition of metals happens, isn't it? Now in the case of copper, you took pure copper as anode and impure copper as cathode, correct? Now passing on electricity, what happens? From this impure copper, what happens? The Cu2 plus will come into the solution, and what happens to this cathode? The pure copper get deposited at the cathode, isn't it? So deposition takes place here in this electrode. Okay, now Faraday is telling how much deposition is taking place. That is, we deal with the Faraday's law. So here anyway deposition is taking place. Okay, now then what happens? Here there is an anode mud. What is anode mud? Anode mud means the soluble impurities that is getting from this anode while dissociation of this copper into copper 2 plus, the soluble impurities which is on the side of the anode is called as the anode mud. Okay, then so this is about the electrolysis of copper or electrolytic refining. Now our interest is what is the reaction taking place at anode and cathode. First we will see cathode. You know what happens in cathode? Reduction. So in cathode what happens? Cu2 plus 2 electrons will give you Cu, correct? Isn't it? And what is anode? Anodic oxidation. That means Cu giving Cu2 plus 2 electrons. So simple. You have already studied all this. Just to get a, I want to make you a recap of this. That's all. Then we will pass on to the Faraday's law. So this is happening, there is a cathodic reduction and anodic oxidation. Okay. So these two reactions are happening in the electrolytic refining of copper. That is why in 10th standard itself in metallurgy, if you are remembering, we studied the most reactive metals. How you refine these most reactive metals? By electrolysis, isn't it? By the electrolysis of the molten chloride. If you remember, for example, sodium, magnesium, etc. You can extract these highly reactive metals by their fused chlorides, that is sodium chloride or magnesium chloride, and aluminium by oxide. We will again see in metallurgy this year, aluminium from bauxite. How will you extract it? Okay. So this is about the electrolytic refining of copper. So you understood? Okay. So that's all. So next class we will see the Faraday's laws of electrolysis. So till then, I just want to say, initially I told you the solution chapter as well as this electrochemistry chapter and the following coming chapter, that is the electrochemistry, solution as well as the kinetics. These three chapters are mainly based on the numericals. So please go through the numericals. Have a thorough knowledge of how to do the numericals. That is very, very important. So please give a stress on numericals. Okay. So that's about this electrolysis of copper or electrolytic refining. Okay. Then now we will see the Faraday's laws of electrolysis. There are mainly two laws, that is Faraday's first law and the Faraday's second law. As I have already told you that this is the quantitative aspect of this electrolysis. So now we will see what is Faraday's first law of electrolysis. Okay. Now Faraday's first law states that the amount of chemical reaction occurs at any electrode during electrolysis, the amount of chemical reaction occurs at any electrode during electrolysis by a current is directly proportional to the quantity of electricity passed. The quantity of electricity passed. See? So, this is Faraday's first law. So, Faraday's first law states that the amount of chemical reaction occurs at any electrode during electrolysis. You know, in electrolysis, the reaction is happening at electrode. We have seen this. Some amount of this reaction happening and the ions are depositing on that electrode. So, that is by a current is directly proportional to the quantity of electricity passed through it. Now, mathematically I can say that this amount of chemical reaction or the mass deposited is directly proportional to the quantity of electricity, that is Q. Isn't it? The quantity of electricity means the quantity of charge which is passed through that electrolyte. This is the first law. So, it states that the amount of chemical reaction occurs at any electrode, that is the mass of the ions is getting deposited. So, that is by a current, for example say I, is directly proportional to the quantity of electricity, or you can say charge, the quantity of electricity or charge passing through that electrolyte. So, mathematically you can write mass or M is directly proportional to Q. Now, what is Q? Q is the charge. Now, if I is the current in time t, how we can write what? M is directly proportional to IT. Correct? Now, changing the proportionality constant, you can say M is equal to Z into IT. See, it's a very important for numerical. That is, M is equal to Z into IT, where Z is called as the electrochemical equivalent. What is it? It is called as electrochemical equivalent. So, M is equal to Z, that is the electrochemical equivalent, into I, which is current, and T in time. So, this is what? This is Faraday's first law. Now, if you want to calculate Z, how will you calculate Z? Electrochemical equivalent Z, that is equal to chemical equivalent by Faraday. This is how you calculate Z. Z is equal to this chemical equivalent by Faraday. Okay. Now, chemical equivalent, how will you calculate? Chemical equivalent is equal to atomic mass divided by X. Last year you have studied this. Chemical equivalent is equal to atomic mass by X. Atomic mass, you know, if you have given copper it is 63, silver it is 108, like that. So, atomic mass, you know, what is X? Now, X depends on, since you are studying an electrolytic cell where oxidation and reduction takes place, the X is the number of electrons that takes part in the reaction. That is X. But X can be, if you talk about acids and bases, X can be the acidicity of a base or X can be the basicity of an acid. So, X depends on the reaction. So, here we have the oxidation reduction reaction. So, X is mainly depends on the number of electrons taking place in the reaction. So, that is how you calculate X. So, chemical equivalent is atomic mass by X. Okay. So, Z is equal to chemical equivalent by F. F is what? F is Faraday. Okay. So, this is the equation for finding out the amount of chemical reaction occurs, or the mass of the ions deposited is equal to ZIT, where Z is the electrochemical equivalent, which can be found by the chemical equivalent by Faraday, whereas the chemical equivalent is equal to atomic mass by X. The X being an oxidation reduction reaction depends on the number of electrons. For example, Daniel cell, what is the number of electrons? 2, isn't it? So, for X, you can write 2. Okay. So, this is all about what? This is all about the first law. Very simple. You just have to study the law, then the equation, and then the application. How you apply this in this oxidation reduction reaction. That's all. Okay. Now, this is the first law. Is it clear? Okay. Now, we will pass on to the second law. Faraday's second law. Okay, clear? Now, what Faraday's second law states as? See, in this 2019-20 board exam, there was one question regarding the Faraday's second law. Okay, that we will come across later. So, Faraday's second law states, Faraday's second law states as the amount of different substances, liberated by the same quantity of electricity passing through the electrolyte is proportional to their chemical equivalent weight. They won't ask you the law, but they will ask you the numericals based on this law. So that is, the second law states that the amount of different substances liberated by the same quantity. See, if that means see, if there are 2 or 3 electrolytic cell in which what happens, the same electricity is passed in connection with this 3 cell, that is in series. You are putting this all the 3 cells in series. The same current of I is passing through it, and at the same time, what happens? The amount of substance which is getting deposited at each electrodes is directly proportional to the chemical equivalent weight of that electrolyte. Which means, for example, in this case, if it is zinc sulfate, now what is getting deposited? For example, if I say zinc plus ion is getting deposited, I can say mathematically the mass of Zn2 plus deposited is equivalent, it's proportional to the chemical equivalent of zinc ion, isn't it? You got it? That is, how much amount of zinc is getting deposited, the mass of the zinc deposited at the electrode can be directly proportional to the chemical equivalent weight. And you know how you calculate the chemical equivalent weight? How is it? That is, chemical equivalent means atomic mass by X, isn't it? Atomic mass by X. What is X? X is the number of electrons taking part in the reaction. So, when 2 or more electrolytic cells are connected in series, having same current, and at the same time, you can say the mass of the different substances liberated. If it is a gas, then it is the pressure you are taking. Okay, this is in the case of solution, you are taking the substance, the amount of substance liberated. Okay, now in the gas, partial pressure we will take. Okay, so the amount of substance liberated by the same quantity of electricity passing through the electrolyte is directly proportional to the chemical equivalent. For example, in here it is copper sulfate and copper is getting deposited. I can write the mass of copper deposited is equivalent to the what? Electrochemical equivalent of copper. Now, if these two are in connection, in series in connection, I can write, for example, M zinc is equal to E of the zinc or proportional to zinc, and M of copper. So, I can write M of zinc by M of copper is equal to E of zinc by E of copper. This is another important equation. You simply write it as M1 by M2 is equal to E1 by E2. So, this is the equation for the Faraday's second law, where E is the electrochemical equivalent. That is atomic mass by X. So, this is about the Faraday's second law. So, you got it? Faraday's first law and Faraday's second law. So, Faraday's first law states what? M is equal to ZIT. Just remember this, then you can write on your own. Second is M1 by M2 is equal to E1 by E2. Okay. So, this is all about the second law. Now, we will see how we apply this Faraday's law onto our electrolytic cell. You know, electrolytic cell, what is happening? Oxidation as well as reduction happens. Now, how we apply this law on this oxidation and reduction? Okay. Then, now is it clear till now? Okay, it's very simple. Now, you are studying in physics also this. Okay. Now, the application or how you apply this in this electrolytic cell is, you know, the amount of electricity you're having an electrolytic cell, no? The amount of electricity or charge, you can say, during an oxidation or a reduction reaction depends on the stoichiometry of that reaction. It's very, very important. What I said, the amount of electricity or the amount of charge that is required for the you are studying the oxidation or the reduction reaction, isn't it? So, in the oxidation or reduction reaction, how much charge is required for that reaction to happen is depending mainly on the stoichiometry of that reaction. Now, example, I can say, citing one example. For example, see, Ag plus 1 electron will give you Ag. We are writing this reduction potential, standard reduction potential, right? Reduction potential you are writing. Now here, what is the stoichiometry? 1. That means 1 electron is required for what? For the reduction of this silver ion, isn't it? Or more precisely, I can say 1 mole of electron is required for the reduction of what? 1 mole of silver ion. Am I right? See, 1 mole of silver ion requires 1 mole of electron for its reduction, isn't it? Then, how I will calculate the charge required for this reduction? How I will calculate? You know, the charge of an electron. The charge of an electron is approximately equal to 1.6 into 10 raised to minus 19 coulomb, right? We have studied last year's structure of atom. So, charge of 1 electron is 1.6 into 10 raised to minus 19 coulomb. Then, how can I calculate the charge of 1 mole of an electron? You know how? Just multiply with Avogadro's number, isn't it? So, that's all last year's chapter. So, Na or Avogadro's number. What is the value of Avogadro's number? That is 6.022 into 10 raised to 23. Isn't it? There. So, Avogadro number into what is the charge of an electron? That is 1.6 into 10 raised to minus 19 coulomb. You got this? That is, it is nothing but all this oxidation reduction reaction, the charge, the quantity of electricity for this reaction to happen depends on the stoichiometry of the reaction. That's all. If it is 2, it's in another case. If it is 3, it's in another case. So, it depends only on the stoichiometry. That's all. Now, in this case, you see 1 mole of electron, listen carefully, 1 mole of electron is needed for the reduction of how much mole of Ag plus? How much mole of Ag plus? That is 1 mole of Ag plus. Now, how will I calculate one charge of 1 mole of an electron? That is just multiply with the Avogadro number. That means this comes to be around 96,500 or 96,484 coulomb. See, this is how you got. This is 1 mole. So, this comes to be the 1 Faraday. Listen, what is 1 Faraday? 1 Faraday is the charge of 1 mole of an electron. Very, very carefully remember, what is 1 Faraday? 1 Faraday is the charge required for 1 mole of an electron. See, in this equation, how many moles of electrons are used for reduction? That is 1 mole of electron. So, how much Faraday? 1 Faraday. You got it? Now, if I say Cu2 plus 2 electrons will give you Cu. If I ask you how much Faraday or how much charge is required for this reduction to happen, you will say 2 Faraday. Why? Because here it needs 2 mole of electron to get reduced for this reaction. You know, for 1 mole it is 1 Faraday. So, for 2 mole it is 2 Faraday. So, in this reaction you require 2 Faraday. Or Al3 plus 3 electrons gives Al. How many moles of electrons are required for this reduction? 3 moles. Now, how much Faraday or how much charge? 3 Faraday. So, that is the application. So, you will know how much Faraday is required or how much charge is required for such reaction to take place. And I am saying these numericals will always come for the board exam. So, please go through the numericals which is having an in-text question on copper, based on copper. So you please do that sum yourself, and if any problem, you just call me or contact me. Okay, so till then, keep studying. Thank you.